Welcome to This Explainer. Today, we're opening up our clean, digital notebook to master the absolute fundamentals of algebraic addition and subtraction, step by step. If you've ever looked at a massive string of letters and numbers and just felt totally overwhelmed, don't worry at all. I'm going to guide you through this like a teacher right beside you, showing you exactly how to untangle these expressions. Let's get started.
Okay, take a look at this fantastic machine of algebraic balance. This really cool diagram perfectly illustrates that algebra is, at its core, just about sorting unknown variables into neat, balanced piles. Think of those gears and funnels as our mathematical rules. That term sorter at the bottom, that is exactly what we do when we combine like terms. We're just putting the x's with the x's and the y's with the y's. It's that simple.
Here's our agenda for today: the algebraic balance machine. Adding expressions together, finding the additive inverse, subtracting algebraic expressions, real-world algebra applications, and a final practice challenge.
Section 1. Adding expressions together, combining like terms.
So when we add expressions, we are carefully grouping our like terms together. Think of it like sorting apples with apples. You obviously can't add an apple to an orange and get two apple oranges, right? In algebra, it's the exact same logic. You cannot combine an x with a y or an a with a b. Now, we actually have two paths to get to the exact same answer here. There's the horizontal method, where we write expressions on one line and group terms left to right, and then there's the vertical method, where we line them up exactly one under the other, just like a traditional addition problem from elementary school. Honestly, neither is wrong. It just depends on how your brain prefers to organize the math.
Let's solve an example together, step by step. Notice how we start by writing the whole expression out horizontally. Now, look at how we group them. We're putting the y variables together in one parenthesis, the x variables in another, and the constants, just the plain numbers, in a third. Now, many students make a mistake in this step by losing a negative sign. So watch really carefully how the minus 3x and minus 2x stay negative inside their specific group. When we add them all up, we get a clean 3y minus 5x plus 4.
All right, now let's find the actual numerical value if x is 3 and y is negative 2. We're just going to substitute. We simply erase the letters and plug those numbers directly into our newly simplified expression. So 3 times negative 2 gives us negative 6. Negative 5 times 3 gives us negative 15, and then we just drop down that plus 4 at the end. Combining negative 6, negative 15, and positive 4 gives us our final, very satisfying result of negative 17.
Section 2. Finding the additive inverse, reversing the signs.
Let's see a quick trick that makes the next part incredibly easy. The crucial concept here is that an additive inverse just means reversing every single sign in the expression. Why? So that when you add them together, they perfectly cancel each other out to 0. If you have a positive, it flips to a negative. If you have a negative, it flips to a positive. It literally is that simple. Time for a quick knowledge check. Pause the explainer right here, grab your own notebook, and try to find the additive inverse for these two expressions on your own piece of paper before I reveal the answer. Remember that flipping rule we literally just talked about?
Okay, let's check your work. By simply flipping the positive 3b to a negative 3b and that negative 2a to a positive 2a, we've found our inverse perfectly. For the second one, positive 5xyz just becomes negative 5xyz. That simple sign flip is the only change you need to make. Great job if you got that.
Section 3. Subtracting algebraic expressions, adding the inverse.
Okay, lean in, because here is the absolute biggest secret in algebra. To subtract, you don't actually subtract at all. I know, it sounds crazy, but you simply change the signs of the expression being subtracted to their opposites, which, yes, is the additive inverse we just practiced, and then you just add that resulting expression to the first one. Why do we do this? Because subtracting a number is mathematically identical to adding its opposite, and addition is just way easier to logically organize without making mistakes. Basically, we turn every single subtraction problem into an addition problem. Now, this is a common exam question, and be careful here, because the phrasing increase of a then b is really just a tricky roundabout way of asking you to calculate a minus b. They are testing your reading comprehension just as much as your math skills here, so always watch out for that wording.
Let's write this whole thing out. Many students make a mistake in this step by forgetting to distribute the negative sign to the entire second expression. So please follow along as we carefully flip every single sign in the second group to its additive inverse. The minus 4 becomes plus 4, the plus 3a becomes minus 3a, and the minus b becomes plus b. By doing this, we're distributing the subtraction across every single term, which ensures proper mathematical balance. Now, it's just a basic addition problem. We group our a's, our b's, and our constants, combining them smoothly to get a final answer of -7a minus 2b plus 9.
Section 4. Real-world algebra applications. Ziad's bag purchase.
Now, you might be wondering, when am I ever going to use this outside of a math classroom? So, let's apply our newly sharpened algebraic skills to a very practical scenario, straight from your classwork. Ziad doesn't have quite enough money for a bag he really wants. The math actually tells a story here. We need to find the exact algebraic difference between the price of the bag and the funds he currently has in his pocket.
Let's map this out. The amount needed is the bag price minus his money. Following our golden subtraction rule, we take Ziad's money and flip every single sign to find the additive inverse. So negative 2y becomes positive, positive 6x becomes negative, and positive 7 becomes negative. We change that minus sign in the middle to a plus, and then smoothly combine the like terms. We gather up the x's, gather up the y's, and gather the numbers to discover he needs exactly 2x plus 6y minus 12 LE to finally buy that bag.
Section 5. Final practice challenge, the triangle perimeter.
All right, here is your final challenge scenario. Imagine a triangular garden fence. We don't have the exact physical lengths quite yet, but we do know the algebraic expressions for each of its 3 sides.
Remember, perimeter simply means adding up all the outside edges. Pause the explainer one last time, grab your notebook, and see if you can calculate the perimeter by adding these 3 algebraic sides together. Take your time, group your terms really carefully, and unpause when you're ready to check your work with me.
Okay, let's check your work step by step. Did you remember to group your terms? By gathering all the x's into one pile, which gives us 6x, then the y's into another pile, which gives us 14y, and the constants into a third, leaving us with positive 2, we get a beautifully simplified perimeter expression of 6x plus 14y plus 2.
Now for the very last and honestly deeply satisfying step of today's lesson. The variables aren't unknown anymore. We're going to substitute 3 for x and 6 for y into that final expression to find the actual real-world physical length of this garden fence. This right here is exactly why we logically simplify our expressions first. It makes plugging in these numbers so much faster and way less prone to simple errors.
Watch this final substitution. When we plug those specific numbers in, well, 6 times 3 is 18, and 14 times 6 is 84, and execute the basic math, we're just adding 18 plus 84 plus 2. That gives us a final perimeter of exactly 104 meters. Excellent job following along with all these steps today. You've successfully taken abstract letters and turned them into a tangible, real-world measurement.
As you leave this explainer today, I want you to think about how mastering the balance of algebraic variables, sorting terms, finding inverses, and systematically simplifying unlocks your ability to calculate and solve massive real-world problems. You now possess the fundamental tools to mathematically model the world around you. So, what are you going to build next? Keep practicing, keep that digital notebook handy, and I will